Okay, go ahead.
Awesome. So hi, everybody, I'm Charlie. I'm on the technical team with Gaia, and here to talk today about wind turbine blade design. If you want to choose that subsystem of the competition. So just a brief introduction overview about wind turbine blade design. These wind powered machines have been around for hundreds of years. And so what the blades have looked like has varied significantly. Initially, when we had big windmills, these sorts of machines use really large surface area blades that were powered using the drag force of air hitting the turbine blade or the windmill blade and then spinning it around. Um, but in today's age, we use turbine blades that are made of airfoils, and these airfoils create lift rather than drag, and this is what powers the turbine and generates torque. So up top here, we can see a bunch of wind turbines, for large scale power generation. And then the bottom, we see the wind day turbine using these sorts of small surface area um, blades. So when you're choosing which airfoil to use, um, like I said, you're trying to maximize the lift and minimize the drag. And so these airfoils, they use the shape of them allows for wind flowing over the top of the airfoil to move faster than below the airfoil, which creates a negative pressure gradient. And so there's a force pushing um, the blade perpendicular to the incoming wind, as you can see in this diagram. So the blade, rather than being oriented this way and then spinning this way, it's oriented this way and spins this way. And so these blades have consist of a bunch of different airfoils of varying sizes, which kind of gives it the shape that we see. And these are optimized to maximize power generation. And so yeah, when you're choosing which airfoil to use, there's a lot of different shapes. These are all defined by your NACA number, which tells you the chord, how arced it is, and the maximum camber, the width. Um, and so as you can see this diagram, the lift
If you
is,
want to actually, I'll reload your slideshow, Charlie. I fixed that diagram.
oh, gotcha. Thank you. Yes, thank you. So the lift is going to be perpendicular to the angle of relative wind, and the drag is going to be parallel to that vector. Um, you and then the quantity or the angle defined between the angle of relative wind and the chord axes is called your angle of attack. And so the angle of attack is changed and optimized for a single airfoil to maximize lift and minimize drag. As that's the goal. That's how you create maximum power. These graphs are generated from airfoiltools.com, which is kind of the go-to source for understanding the differences in lift and drag for a certain angle of attack. And so the one of the most important graphs to look at is this one on the bottom left, the coefficient of lift versus coefficient of drag versus the angle of attack. So as you can see, there's a certain angle. This is about 5 degrees that generates the maximum ratio of lift to drag. And so you'd want to be optimizing um, your blade to have that angle at the specific part of your blade. When you're using this tool, you should select a low Reynolds number, because there's a low wind speed in Peru where we're getting putting these wind turbines. Um, and yeah, you can see, yeah, like I said, you want to optimize the coefficient lift over coefficient drag. Another important um, quantity to understand when you're talking about wind turbine blade design is the tip speed ratio. And we talked about this a little bit in our electronics presentation, but this is the ratio of the tip speed of the blade relative to the incoming wind speed. And so you can kind of control this when you're controlling how fast and how you want the power to be manifested in the power generation, um, with how quickly you want the wind turbine to spin. You can see with like turbines with the higher swept area, like the ones we showed before with the Ford blades or the dozen blades, they are optimized. They work best at a low tip speed ratio. And so these are high torque machines where it rotates slowly, but has a significant amount of torque versus Graph E, which is what the wind day design is, a two-bladed turbine it is optimized for between 7 and 8 tip speed ratio. So it's going to be spinning a lot faster, which is an important thing to keep in mind, especially when you talk about later the equations that go along with how you want to design your blade. I'll talk a little bit about rotations and angles. There's a lot of different rotational frames of reference you should be thinking about when you're understanding how the blade moves. Firstly, just of course the blade rotates around the hub, around the nacelle. Secondly, the hub will rotate itself in order to face the direction of wind. And then the important quantity for blade design is the pitch of the blade. And so this is the angle of twist that the blade is. And so the blades can be pitched like an airplane wing if you want to, in a way that optimizes the power generation. And you can also control the speed of the blade by pitching it in a certain direction. And so because of the relative, sorry, I'm having time explaining this, but because of the blade, a point at the tip of the blade as it rotates will be rotating at a higher relative velocity than a point closer to the hub. That vector will create a different relative speed of not only the wind coming into the face of the turbine, but also the turbine itself moving. And so this creates a diagonal vector, as we can see here. And so there's a more shallow, as the blade moves slower, there's a more shallow pitch angle. Not pitch angle, just an angle of relative wind versus further out to the tip. What that relative vector would be. And so because of this, because the blade itself is seeing different relative wind, there has to be a twist along the blade if we want to maintain a constant angle of attack, as we saw in these graphs. If we want to maintain the 5-degree alpha value, the pitch angle at near the hub has to be different than the pitch angle at the tip. And so this creates a twist along the blade as well. And so you see these on the turbines, and we see a slight twist along the wind day turbines as well. This angle is defined as phi, as phi, as 2/3 of the arctan of 1/, the local tip speed ratio. Which makes sense as the local tip speed ratio will change along the blade as that relative velocity at those points changes as well. So next we'll talk about chord length. I kind of mentioned this before, but the chord length is the length of the cross section of the turbine blade. So this is important because it changes the aerodynamic efficiency depending on how large the chord is. And so a good rule of thumb is that the larger the chord is, the more power will be generated. But the issue is that creates more material needed. It's heavier, it might be more prone to breaking. And so that has to be optimized in a way such that not only aerodynamically efficient, but also structurally efficient. But the equation used in industry to calculate the optimized chord length is this shown here. And so this depends on where the radius along the blade you are, the number of blades, the lift coefficient we determined before from the online resource, and then your relative angle of wind, or of your pitch angle. And so from this you can find an optimal chord length that will generate the maximum amount of power. And lastly, the blade
I have
length.
a quick question.
Yeah, please.
Can I ask a quick question? It's about the the twist that you mentioned in the pitch part.
Mhm.
Yeah, this one. I'm wondering, so it's kind of like uh there's a twist force moving like the wind turbine here. It's kind of like moving it to the right?
Would you ask if there's a force?
Yeah.
No, sorry. So it's not a force. It's more of a, you always want to maintain the same angle of the cord relative to the direction of wind. And so because further along the turbine, that relative angle changes, you have to compensate for that by twisting the blade. So it can't have a constant angle. It has to change as it goes along the length of the blade. Is that a good explanation, Becca?
Yeah, I think it is. And maybe what you were thinking of that might have been interpreted as a force was those arrows on the picture. Those arrows are representing the velocity, the magnitude of the velocity vector at different spots along the blade. Because way out at the end of the blade near the tip, it's going to be spinning a lot faster because you've also got that rotational velocity in addition to the wind velocity. And the difference
Okay.
of the magnitude and direction of that velocity is why you need this static geometry change of like the angle that the airfoil is pointed statically as you go across the blade.
Oh, okay. I got it. Yeah, thank you.
Cool. No, thanks for the question. Um, yeah, so then and blade length, this like the cord length somewhat. This more generally, the longer the blade is, the more power you'll be able to generate. Um, this is the quantity used is typically the rotor diameter, and so the diameter of the circle of the swept area of the blades. Um, yeah, as you can see, but yeah, however, the as the weight goes up, the price goes up, and as the blade goes up, the weight exponentially goes up because you need more structure. The bending moment is larger. Obviously more material, and so you kind of that's another optimization or trade-off is how much power do you want to generate versus how much you're going to spend on the blade to reinforce it. And so along those lines, the kind of rule of thumb, like the wind maximum potential wind power you can generate from a turbine is defined as the 1/2 the density of the air times the area of the swept area of, so that would be pi times the blade length squared, times the cube of the incoming wind velocity. And so this is just a geometric, physics based. You can check the units, how much power is going through that area. And so the important thing to note about this is that as the blade length increases, the area will increase to the square of that. And so you get much more power. But then also this also shows the importance of how it like the velocity. So the wind velocity, just you can get so much more power in a windier spot, which makes sense, but I think it's important to see that mathematically. Um, however, this is the amount of power going through that area. The maximum amount of power that can be extracted from that area is called the Benz limit. And so the Benz theory, I won't go through the derivation, but that uses conservation of mass momentum and then the underlying idea that as wind passes through that area, it can't if it completely came to a stop, that would be you could extract the maximum amount of power from that. But in order for wind to continue, like conservation of mass, for the air to continue flowing through that area and make the turbine spin, there's a fairly simple derivation you can Google, and then the maximum power that can be generated is 59.3%. And so like that's 59.3 times this power generated here. Just as a frame of reference.
One thing I'll add on to that previous slide is that the power equation, the velocity that you put into that is an instantaneous velocity. You can't put the average velocity into that equation and get an average power, because the cube of an average is not the average of a cube, if you think about how statistically it works. So if you're trying to get the average power for a whole set of velocities, you might have a time series for, you know, what a standard hourly velocity profile over time is in Peru. Then you'd either need to use a different formula that takes that into account, that uses like the distribution statistically, like the properties of the CDF of that wind power distribution, or probably the simpler way is just calculate this power individually for each velocity in your hourly time series and then take the average at the end. You can't take the average of the velocity at the beginning. And yeah.
Yeah.
And I guess also bets with a T for those who want to Google it.
Yes, thank you. Yeah, thanks. See, I'll talk about different trade-offs in terms of, you know, like I kind of talked about before. So in terms of the blade length, you want it to be longer. However, you can't be too long where it would cost too much to like be built. But kind of things that the competitors might find more important is the flexibility. And so there's a lot of studies that show that the more flexible a blade is, it will increase the power generated of the turbine. Again, I haven't gone into the derivation of that, but that's a kind of an accepted fact. And so, but you can't have that be too flexible such that the blade tip deflection causes the tip to hit the tower below the turbine. And another one might be the decreased weight. Also, the different decreased weight, so choosing a material that's lighter allows the turbine to spin faster, coinciding with increased power generation. But this typically decreases strength in the lifespan. And so you kind of want to optimize the amount of tip blade deflection that you have, while also finding a material that's both you know, not too expensive, but it also is strong. But maybe it might also have a low density, a light blade. Do you want to talk about this blade, Becca, or this slide?
Yeah, so because the point of the competition is to improve from a baseline, it's really important to understand the current design that WindAid uses. And so WindAid has had this design for years. They honestly didn't really know how it performed aerodynamically until recently. A student did their thesis and went through the numbers and found out that actually WindAid's current design is pretty close to what is aerodynamically optimal. So that green line is pretty close to that black dashed line. And that thesis is Santiago's thesis. You can find it in the technical resources spreadsheet. And so, in fact, WindAid sort of was expecting initially that there might be a lot of room for improvement in the aerodynamics, but now that we actually have the data for how their current blade performs, there's not that much room for improvement aerodynamically. And so Airbus was working with WindAid, and instead of trying to improve aerodynamically, because there's not much room for improvement there, they were thinking, what if we improved the structural integrity? And so they have that design that is the red curve that they worked with WindAid to build, that sacrifices the aerodynamic performance a little bit, but has better structural. The problem with that though is that Windade hasn't actually observed any structural issues with their current blade. And so it doesn't necessarily make sense to be sacrificing the power output for the sake of improved structures when you aren't really having any structural problems. And this isn't making the blades any cheaper. It isn't making them any easier to manufacture. And those are what Windade would actually care more about improving. And so I'll refer you to the thesis that's again listed in that technical resources spreadsheet to understand how these curves are calculated. But basically it's power as a function of tip speed ratio coming from all the aerodynamic data, like the airfoil coefficients of lift and drag and angles across the blade. But then on the next slide, what would actually be helpful for Windade is to reduce the cost, simplify the manufacturing process while keeping the power generation roughly the same as it is. And so it might be necessary to make like minor sacrifices in the power generation to achieve the objectives of reducing costs and simplifying manufacturing. And that's okay, but we don't want the power generation to go down like a substantial amount.
Yeah. So then I can run through just kind of a little bit of the process of what Windade's doing now, which we hope to optimize and make better. We're still learning this. We have a team in Peru right now working on understanding their process. And so we'll have more information later about where the actual issues are and what can be improved. But this is just a general understanding of the manufacturing process. So they have two kind of main components of the blade. There's the foam core in the middle, and then the resin which goes on the outside. Both of these are made using molds they have, which are, they have to optimize what they deem to be the appropriate shapes for the blade. The process is, as you read here, they cut out two fiberglass blade outlines using a stencil. They put plastic on the molds. They insert a metal bar and fiberglass into the mold, bolt it closed, and then inject the foam. So this foam sets for 6 hours. We're still kind of trying to understand how long this whole process takes. We know that there's issues with the metal bar, manufacturing itself, like process itself that's there for structural support. But that's kind of a main component of the central layer of the blade. And then so we also have the resin portion of the blade. And so to create that same molding manufacturing process, you wax the mold, cut form and adhere the carbon fiber to the foam core created here. Insert the foam core into the mold with two fiberglass cutouts. Close the mold. Set of the vacuum resin injection rig, which is kind of a typical injection molding technique where you extract all the air. And then let the rig run for 20 minutes and then let the mold set for 24 to 40 hours, as you read here. So this kind of, two-step process to create the blades. We know it kind of takes a long time. It's somewhat costly. As I said, we're trying to figure out those numbers to get to use it. If you want to choose the subsystem, those would be important values to have. Yeah, like I said, we know that for example, we heard that the metal bar takes half a day to bend and hammer into place to go in the foam core. And so if we find a better way to structurally support the foam core without needing this half day long process that they wouldn't have in Peru, that might be important. And so let me point to just where I got this information from in the technical resources document you have. Just so you know how to use this. As we can see, we can look at the titles, Windade CAD file, Windade blade manufacturing video, and wind turbine fabrication document presentation. And so this will link you here, the turbine fabrication. And then there's also a document. Actually, I don't know if this is on here. Do you know if this is back at the manufacturing
It's
guide?
linked on the problem statement and not in the technical resources, but that's a good point. We could add it to the technical resources too, so it's all in one place.
Got it. Well, so that, yeah, I'll say you can find that on this document. I'll link it there after they make give this presentation. But there's more thorough, some of it's in Spanish, but the materials used, such as the fiberglass, carbon fiber, metal sheet, tape, the corks, the plastic bottles, as well as the foam core and resin mold. Yeah, resin, manometer, peroxide. And then a more thorough explanation of how these are manufactured. And so we'll give some more resources to this if we see a lot of interest in wanting to optimize this process.
Yeah, and especially to optimize the cost of the blades, it'll be important to understand the current cost drivers of that system. And so far, Windade hasn't been able to give us those numbers, but they're working on it. And so definitely when we receive the cost breakdown for the blade subsystem specifically, we'll post those as another technical resource. The cost breakdown for the other subsystems, everything we have, is already linked in that spreadsheet again, but just we don't have anything more detailed about the blades, about what the drivers are for within the blades.
Yeah, so lastly, let's talk about the the testing we're gonna do with these blades. Because we're not necessarily asking you to optimize the power output, but rather the manufacturing process and cost breakdown. It might be more of a report sort of format. However, if you want to be testing the power generation for the blades you have, you might use a wind tunnel test. Actually, yeah, do you want to go with this, Becca?
Yeah, so the wind tunnel testing, if your team decides to pursue that, like within your university, would mostly be with the goal of how much of a performance hit are we taking by making whatever modifications that we have decided are important for cost and manufacturing process improvement. And so a wind tunnel works by blowing air at the thing. But in order to have consistent dynamics, because dynamics are driven by Reynolds number, if you make the size of the blade smaller, the only way to make up for that while keeping the Reynolds number consistent would be to make the velocity higher, unless you're going to like change the fluid to not be in air, but that's pretty impractical. And so it can be difficult to have high enough speeds to maintain the velocities required. And just based on facilities, Cornell has a smaller size wind tunnel, which means that the velocities are going to have to be a lot bigger, whereas MIT's wind tunnel is a little bit larger, so the velocity wouldn't be as extreme needed for small scale testing. But what you would be doing in a wind tunnel test is you want to measure the torque being exerted on the system. And so you're going to want some sort of torque sensor. And one word of warning with any sort of scaled down testing is that friction of setup, like if you've got bearings or whatever, at small scale can play a more dominant role than you would expect compared to a large scale. And so just be careful that you're not unintentionally biasing the test with the effect of some aspect that would not fully be present at larger scale, like additional friction in a drivetrain. And so we'll be releasing more specifics on how evaluation will happen on the competition side for the blades. This is more for your reference of throughout your design process if you want to be validating your design.
Cool. What's
And
all
I guess
have?
I can mention people have often like sort of brainstormed the idea of like, oh, can you put the blades on a car, like strap them to a car and then drive the car at speed so you can get whatever speed you want, controllable without the facilities or effort required with a real wind tunnel test. And so that is a possibility. Like sure you can do it. It's just difficult to get the right quality of data because if the turbine is strapped to a car, the car is going to mess a lot with the airflow. And that can definitely affect the results because the amount of lift produced on those blades comes from the pressure difference of the wind going over the airfoil of that specific shape. And if you've now also got the shape of the automobile relatively close to it, there's a boundary layer, there's all sorts of turbulence, like just stuff that can mess with it. And so if you want to pursue that, be very careful about it to make sure that any data you collect is not just going to be garbage.
Yeah. Yeah, so that's all I have to present. Anything else, Becca? Or any questions?
Yeah, I think the main thing I'll emphasize is for blades, definitely read through the thesis that I was referencing, Santiago's thesis, because that does a very good job of outlining the process for like how do you even determine what the optimal shape is and how close one day's design is to optimal and trading off the structures versus the aerodynamics and everything like that. So that's a really good reference. And there's also a portion of that thesis that is not very relevant that talks about what if you, instead of using standard composite materials, if you instead use like an organic composite. And that is, I guess teams are like also free to suggest that. But it's not necessarily a scope that WindAid is like looking to move to. But it is more sustainable materials wise. So it can have benefits to use like a fiber instead of the composite. Or the, yeah, the foam.
Yeah. Cool.
We have a
Awesome.
question. Is the article you showed before for reference?
The article,
Are you referencing Iris the like WindAid document or?
or the Santiago?
No, yeah, I just want to double check. Uh, the one you said like with the thesis one is like
Oh, the thesis. Yeah.
specifically like
Control F in there for thesis,
yeah.
Charlie, and it'll come up. Yeah.
Yep. So right here, number 16. University thesis describing Airbus blade design. So I'll click on it and see what it looks like. Yep. Cool. Well, I appreciate you logging on and asking questions. And I hope the viewers at home find this helpful.
Yeah, thanks for coming. And hopefully more people are able to watch the recording as well.
No problem. Thank you, guys.
All right. Thanks.
Have a good night.